In section 8.1, one of our examples, example 2, involved straight and semicircular beams, and we found expressions for n, v, and m as continuous functions of position along the beam, in terms of x for the straight section or theta for the curved section. We'll now focus exclusively on straight beams and also focus exclusively on the equilibrium approach. Because we are constructing internal loads as a continuous function of position, this now involves not a single free body diagram, but sets of free body diagrams. We'll assume we have a traditional XY coordinate system anchored at the left end of the beam, and that there are a variety of discrete and continuous loads between its ends. Several important points need to be made before we begin looking at examples. It is crucial that the coordinate system be anchored at a location, typically the left end as shown here. We can't move the coordinate system around for different intervals of interest. Position x actually has two different meanings. The obvious meaning is that x reflects a local position of interest, but x also reflects a global feature. When we isolate a section of the beam, we are capturing everything between the origin and the local position. In this sense, x also represents the size of the enveloping surface used as the basis for the free body diagram. Whenever there is a sudden change in the nature of the loading as we move along the beam, we need a new set of free body diagrams to capture this change. In the illustration sketched here, we actually need 4 sets of free body diagrams. One set before the discrete load, one set between the discrete load and the start of the distributed load, a third set within the distributed load, and a fourth set after the distributed load ends. Thus, in most cases, we are not just examining sets of free body diagrams, but discrete sets of continuous sets of free body diagrams. Before starting a problem with the equilibrium approach, one of the first things we should do is indicate how many discrete sets we'll need. This slide summarizes many of the points we just made. In particular, the third and fourth bullets refer to the need for discrete sets of continuous sets of free body diagrams. A current set of free body diagrams is valid until the sudden appearance of a new discrete or continuous load renders it invalid. Then a new set, an additional cut, is needed. One additional point needs to be made here regarding continuous loads, and you can refer back to the third set of free body diagrams in our opening illustration at your convenience. We saw in Chapter 7 how to convert continuous loads into equivalent discrete loads at their effective centers, and we'll want to do that again here. However, it is extremely important to keep the distributed load intact until after we've made the cut and drawn the original free body diagram. Then we can make a conversion to an equivalent discrete load, and we'll see examples of how to do that shortly. The first bullet in this slide reiterates the importance of anchoring the coordinate system in constructing the internal force expressions. The second bullet addresses the issue of sign convention we'll use for two-dimensional straight beams. In discussing this in section 8.1, we pointed out that the sign convention for positive V in two-dimensional beams is the one exception we'll adopt in our general rule involving coordinate directions and faces. That is, the left figure in B shows V in the negative y direction on a positive face, and the right figure in B shows V in the positive y direction on a negative face. We said we would ordinarily think about such a force as negative. Most of our applications, however, are going to involve loads on structures due to gravity, which obviously points down. If we talk about a uniform distributed load of, for instance, 1 kip per foot, it will be assumed that it is already pointing in the negative y direction. The note below the figures in B emphasize this point. In this way, the sign convention for shear force V is consistent with the sign convention for distributed load W. When writing equilibrium equations based on our free body diagrams, the signs given to loads depend on their direction relative to the established coordinate system, not their sign convention. For instance, if we were writing equilibrium equations for the left figure in B, the shear force would appear as minus V in the y component force equation. If we were writing equilibrium equations for the right figure in B, the axial force would appear as minus N in the x component force equation. The fact that both forces are considered positive is irrelevant. We are writing the equations in the fixed coordinate system, and it is their direction in that system that determines their signs in the equilibrium equations. With these preliminary remarks in mind, we are now prepared to look at some examples of constructing continuous functions of n, v, and m based on the equilibrium approach. We'll go through each of these examples in detail, but let's begin with some broad observations. In example 1a, we have a cantilevered beam with a single discrete load at its end at x equals 0, and no additional loads between its end and its built-in support. We should be able to construct our expressions for internal loads on the basis of a single set of free body diagrams. In example 1b, we have modified the problem in 1a by adding an additional discrete load halfway between the end and the built-in support. The sudden appearance of this discrete load at L over 2 means we'll need two sets of free body diagrams, one for x less than L over 2 and one for x greater than L over 2. In example 1c, we have a uniform distributed load across the beam, but a roller support at B before we get to the end of the beam. The sudden appearance of a discrete force requires an additional set of free body diagrams. It doesn't matter whether the discrete force comes from an external load, as in example 1b, or a support reaction, as in example 1c. Therefore, we'll also need two sets of free body diagrams for example 1c. One for x less than 16 meters, and one for x greater than 16 meters. Those of you who are mathematical purists may wonder what happens exactly at x equals L over 2 or x equals 16 meters. We won't concern ourselves with this other than to say the appearance of discrete loads gives rise to a variety of discontinuities which we'll observe shortly. A second issue is whether we should begin by solving for reactions at the supports. We can construct our internal force distributions without doing so for examples 1a and 1b, but these problems are sufficiently simple that we can note on the figures what those reactions would be. Vertical force equilibrium will require a reaction here equal to P, and also a moment reaction equal to P times L. For 1b, vertical force equilibrium will require a reaction equal to 2p and a moment reaction equal to 3/2 PL. In contrast, we absolutely need the reactions for A and B as a precursor to finding internal loads for problem 1c. Now let's examine problems 1a and 1b. As we mentioned, we need just a single set of free body diagrams for example 1a. We're cutting through the beam at some arbitrary position x, and using our sign conventions, our internal loads will be designated this way. Horizontal force equilibrium will simply give us that the normal force is 0. In fact, in the problems we're going to be doing, we're going to be focusing on those internal forces, V and M, that are associated with lateral deformation. So even though N is present or possible, going forward we will generally exclude N. Even though it's there, it's not the important part of the problem. Vertical force equilibrium gives us minus P minus V of x is 0, or V of x is minus P. Finally, there are two natural places for us to take moments, either about the origin A or the cut plane X. Either one will give us the same result. I'll choose to take moments about A and set that equal to 0, in which case we have m of x minus v of x times x equals 0, or m of x equals v of x times x, but v of x is minus p, so m of x is minus px. After we've established expressions for our shear force and bending moment, it's traditional to sketch them, even though the results aren't very interesting here. In the case of v of x, we have that it's just a constant equal to minus p. And in the case of m of x, we have the equation for just a straight line, which starts at 0 at x equals 0 and reaches a peak value of minus pl. At the end. One of the things to note here is the connection between v of x and m of x at the end of the beam and the reactions that we established earlier. We found that our reactions had to look like this at the end of the beam. We have a vertical reaction force of P, and we have a clockwise reaction moment of PL. Notice that given our sign conventions, our results for V and M at the end of the beam are completely consistent with those reactions. V is minus P, but V's sign convention is positive down, so a V of minus P is equivalent to a force up equal to P. Bending moment M has a sign convention that's positive counterclockwise. Our result here tells us that M of x goes to minus PL, which is a clockwise moment PL. This is actually a very important feature that will be important to us as we get to more complicated problems. We should find as we move from left to right across the beam that when we get to the other side, our results for V and M are consistent with the reactions or the absence thereof that we expect at the end of the beam. Now we move to example 1b. Here we have two sets of free body diagrams, one for x less than L over 2 and a second for x greater than L over 2. We might note that for x less than L over 2, the free body diagram looks like this. Again, I'm going to ignore the axial force N from here on out. And we might note that this looks identical to the free body diagram we had in example 1a. We could go ahead and write our equilibrium equations again, but we would get exactly the same results for 1a. So I'm just going to say here that this is the same as 1a. That is, we know that for x less than L over 2, v of x is minus p, and m of x is minus px. The second set of free body diagrams look like this. Now our vertical force and moment equilibrium equations give us minus 2p minus v of x is 0, or v of x is minus 2p and sum of the moments about a equals 0 gives us minus p times L over 2 from the intermediate discrete force plus m of x minus v of x times x is 0. But we know what v of x is, so we'll move these terms over to the other side, and we have p times L over 2 minus 2px. So our results for x greater than L over 2 are that v of x is minus 2p and m of x is p L over 2 minus 2px. Now we'll just make a note here. Again, even though our results are for x less than L over 2 and x greater than L over 2, let's just consider what m is at x equals L over 2. According to this expression, it's p L over 2 minus 2p times L over 2, which is p L over 2 minus pl, which is minus p L over 2. Notice that that's exactly the same value that m will have from the first set of free body diagrams as we approach L over 2 from below L over 2. The result of this is to give us shear force and bending moment diagrams that look like this. We have v as constant and equal to minus p before we get to L over 2. And we have v is equal to minus 2p after we pass through L over 2. It is not an accident that the size of the jump here is directly related to the size of the discrete force that's applied there. A sudden force of magnitude p appears at x equals L over 2, and the shear force distribution jumps down by that amount. Note also once again that we find that as we move over to x equals L, the value of V is minus 2p. Given our sign convention, that's equivalent to 2p pointing up, and that matches the force reaction at the built-in support. We can also construct our expression for the bending moment. We have for x less than L over 2 that m is equal to minus px. So we'll have a straight line with a value that approaches minus p L over 2 as x approaches L over 2. We have an alternative expression for x greater than L over 2, but we notice that it takes on the same value as x approaches L over 2 from above L over 2. The slope of that expression is also twice what we have for the case of x less than L over 2. That is, the slope is minus 2p instead of minus p, and we'll find that at x equal to L, we get a value of minus 3p L over 2. Once again, it is not an accident that the value of the bending moment at x equals L exactly matches the reaction moment that we expect at the built-in support. Notice that the appearance of the discrete force at L over 2 has given us a discontinuity in V, but not a discontinuity in M. However, it is the case that we have a kink in the m of x curve at x equals L over 2. So even though we don't have a discontinuity in M, we do have a discontinuity in the slope.